Welcome to Tech Girl Kannada YouTube channel. Module 3 Basic Structures of Computers, Instructions and Programs. Introduction. Computer organization explains the function and design of the various units of digital computers that stores and process information. It also deals with the input units of the computer which receive information from external sources and the output units which send computer results to external destinations. The input storage, processing, and output operations are governed by a list of instructions that constitute a program. It deals with about the computer hardware and computer architecture. Computer hardware consists of electronic circuits, magnetic and optical storage devices, displays, electromechanical devices, and communication facilities. Computer architecture encompasses the specifications of an instruction set and the functional behavior of the hardware units that implement the instructions. Classes of computers: desktop or laptop computers, general purpose, variety of software subject to cost and performance trade off. Workstations, more computing power used in engineering application, graphics, enterprise system, mainframes, server computers, low end range, supercomputer, embedded computers, and so on. Functional units. Computer consists of 5 functionally independent main parts: input, memory, arithmetic and logic unit, output and control units as shown in the figure. Memory, input, output, interconnection network, arithmetic and logic, control. The input unit accepts coded information from human operator using devices such as keyboards or from other computers over digital communication lines. The information received is stored in computer's memory either for later use or to be processed immediately by the arithmetic and logic unit. The processing steps are specified by a program that is also stored in the memory. Finally, the results are sent back to the outside world through the output unit. All of these actions are coordinated by the control unit. An interconnection network provides the means for the functional units to exchange information and coordinate their actions. Input units. Computer accepts coded information through input units. The most common input device is the keyboard. Whenever a key is pressed, the corresponding letter or digit is automatically translated into its corresponding binary code and transmitted to the processor. Many other kinds of input devices for human computer interaction are available, including the touchpad, mouse, joystick, and trackball. These are often used as graphic input devices in conjunction with displays. Then, microphones can be used when to capture audio input which is sampled and converted into digital codes for storage and processing. Similarly, cameras can be used to capture video input. Digital communication facilities such as the internet can also provide the input. Digital communication facilities such as the internet can also provide input to a computer from other computers and database servers. The function of the memory unit is to store programs and data. There are 2 classes of storage called primary and secondary. Primary memory, also called as main memory, is a fast memory that operates at electronic speeds. Programs must be stored in the memory while they are being executed. The memory consists of large number of semiconductor storage cells, each capable of storing 1 bit of information. These cells are rarely read or written individually. Instead, they are handled in groups of fixed size called words. The memory is organized so that the one word can be stored and retrieved in one basic operation. The number of bits in each word is referred to as the word length of the computer, typically 16, 32, or 64 bits. To provide easy access to any word in the memory, a distinct address is associated with each word location. Addresses are consecutive numbers starting from 0 that identify successive locations. A particular word is accessed by specifying its address and issuing a control command to the memory that starts the storage or retrieval process. Instructions and data can be written into or read from the memory under the control of the processor. It is essential to be able to access one word, any word location in the memory as quickly as possible. A memory in which any location can be accessed in short and fixed amount of time after specifying its address is called random access memory. RAM. The time required to access one word is called the memory access time. This time is independent of location of the word being accessed. Typically ranges from a few nanoseconds to about 100 nanoseconds for current RAM units. Cache memory. As an adjacent to the main memory, a smaller, faster RAM unit called a cache is used to hold sections of the program that are currently being executed along with any associated data. A cache is tightly coupled with the processor and is usually contained on the same integrated circuit chip. The purpose of the cache is to facilitate high instruction execution rates. At the start of the program execution, the cache is empty. All program instructions and any required data are stored in the main memory. As execution proceeds, the instructions are fetched into processor chip and a copy of each is placed in the cache. And the execution of an instruction requires data located in the main memory. The data are fetched and copies are also placed in the cache. Secondary storage. Primary memory is essential. It tends to be expensive and doesn't retain information when power is turned off. Additional, less expensive permanent secondary storage is used for when large amounts of data and many programs have to be stored, particularly for information that is accessed infrequently. Access time for secondary storage are longer than the primary storage. Memory, a wide selection of secondary storage devices is available, including the magnetic disks, optical disks, DVDs, and CDs, and flash memory devices. Arithmetic logic unit. Most computer operations are executed in the arithmetic and logic unit of the processor. Any arithmetic or logic operation such as addition, subtraction, multiplication, division, or comparison of numbers is initiated by bringing the required operands into the processor where the operation is performed by the ALU. For example, if two numbers located in the memory are to be added, they are brought into the processor and the addition to carried out by the ALU. The sum may then be stored in the memory or is retained in the processor for immediate use. When operands are brought into processor, they are stored in the high-speed storage elements called registers. Each register can store one word of data. Access times to registers are even shorter than access times to the cache unit on the processor chip. Output unit. The output unit is the counterpart of the input unit. Its function is to send processed results to the outside world. Familiar example of such a device is printer. Most printers employ either photocopying techniques as in laser printers or inkjet streams. Such printers may generate output at speeds of 20 or more pages per minute. However, printers are mechanical devices and as such are quite slow compared to the electronic speed of the processor. Some units such as graphic displays provides both an output function showing text and graphics and an input function through touchscreen capability. Control unit, the memory, arithmetic and logic and IO units store and process information and perform input and output operations. The operation of these units must be coordinated in some way. This is the responsibility of the control unit. The control unit is effectively the nerve center that sends control signals to other units and senses their states. IO transfers consisting of input and output operations are controlled by program instructions that identify the devices involved in the information to be transferred. Control circuits are responsible for generating the timing signals that govern the transfers and determine when a given action is to take place. Data transfers between the processor and the main memory are also managed by control unit through timing signals. A large set of control lines wires carries the signals used for timing and synchronization of events in all units. The operation of computer can be summarized as follows. The computer accepts information in the form of programs and data through the inputs units and stores it in the memory. Information stored in the memory is fetched under the program control into an arithmetic and logic unit where it is processed. The processed information leaves the computer through an output unit. All activities in the computer are directed by the control unit. Basic operational concepts. The program to be executed in the stored in the memory. Instructions are accessed from memory to the processor one by one and execute a step for instruction execution. Consider the following instruction: add, locate, add not. This instruction is in the form of the following instruction format: opcode, source, destination, where add is the operation code, locate is the memory operand, and add not is the register operand. This instruction has the contents of memory location A with the contents of register R0 and the result is stored in the R0 register. The symbolic representation of the instruction is R0 is equals to locate plus R0. The contents of memory location, locate and register R0 before and after execution of the instruction is as follows. Before instruction execution, locate 23H, R0 is 22H, locate is 23H, but after instruction execution, R0 will be 45H. The steps for instruction execution are as follows. Fetch the instruction from the memory into the instruction register in CPU. Decode the instruction 111110000010011010. Access the memory operand, access the register operand. Perform the operation according to the operation code. Store the result into the destination memory location or destination register at R1, R2, R3. This instruction is in the form of the following instruction format: opcode, source 1, source 2, destination, where R1 is source operand 1, R2 is the source operand 2, R3 is the destination. This instruction adds the contents of register R1 with the contents of register R2 and the result is placed in R3. Symbolic representation of this instruction is R3 equals to R1 plus R2. The contents of register 1, R1, R2, R3 before and after execution of this instruction is as follows. Before instruction R1 24H, R2 34H, R3 is 38H, and here after instruction execution, R1 and R2 will be same, but R3 will be modified to 58H. Computer organization, the steps for instruction execution is as follows. Fetch the instruction from memory into IR. Decode the instruction. Access the first register operand R1. Access the second register operand R2. Perform the operation according to the operation code. Store the result into destination register R3. Connection between memory and processor. The connection between memory and processor is as follows in the figure. The processor consists of different types of register: MAR, memory address register; MDR, memory data register; control unit; PC, program counter; general purpose registers; IR, instruction register; ALU, arithmetic and logic unit. This is the diagram of basic computer organization. That is memory, MAR, PC, IR, MDR, R0, R1 to Rn-1, and general purpose registers, control, ALU, processor. The functions of these registers are as follows. MAR, it establishes communication between memory and processor. It stores the address of the memory location as follows in the figure. MAR 500H, memory location 5023H, 5001, 43H, and something. MDR, it also establishes communication between memory and the processor. Stores the contents of the memory location data. Written into or read from memory as shown in the figure 23H. Control unit controls the data transfer operations between memory and the processor. It controls the data transfer operations between IO and the processor, IO and the devices. Generate control signals from memory and IO devices. PC, program counter, it is special purpose register used to hold the address of the next instruction to be executed. The contents of PC are incremented by 1 or 2 or 4 during the execution of the current instruction. Contents of PC are incremented by 1 for 8-bit CPU, 2 for 16-bit CPU, 4 for 32-bit CPU. General purpose register or register array. The structure of register file is shown in the figure R0 to Rn-1. Consists of set of registers. A register is defined as a group of flip-flops. Each flip-flop is designed to store 1 bit of data. It is a storage element. It is used to store the data temporarily during the execution of the program. It can be used as pointer to memory. Register size depends on the processing speed of the CPU. Example, register size is 8 bits for 8-bit CPU. IR, instruction register, holds the instruction to be executed, notifies the control unit, which generates timing signals that controls various operations in the execution of that instruction. ALU, arithmetic and logic unit, performs arithmetic and logic operations on given data. Step for reading and the instruction. PC contents are transferred to MAR and read signal is sent to memory by control unit. The data from memory location is read and sent to MDR. The content of MDR is moved to IR. PC, MAR, memory, MDR, IR, CU, read signal. Bus structure. Bus is defined as set of parallel wires used for data communication between different parts of computer. Each wire carries one bit of data. There are two types of buses, namely address bus, data bus, and control bus 1. Address bus, it is unidirectional. The processor CPU sends the address of an IO device or memory device by means of the bus. Data bus, it is bidirectional bus. CPU sends data from memory to CPU and vice versa, as well as from IO to CPU and vice versa by means of this bus. Control bus, this bus carries control signals for memory and IO devices. It generates control signals for memory named MEMRD and MEMWR, and control signal for IO devices namely IORD, IOWR. The structure of single bus organization is as shown in the figure. Input, output, memory, processor. The IO devices, memory, and CPU are connected to this bus as shown in the figure. Establishes communication between two devices at a time. Features of single bus organization are less expensive, flexible to connect IO devices, poor performance due to a single bus. There is a variation in the devices connected to this bus in terms of speed of operation. Few devices like keyboard are very slow. Devices like optical disc are very faster. Memory and processor are faster, but these devices uses the same bus. Hence, to provide the synchronization between two devices, a buffer register is attached to each device. It holds the data temporarily during the data transfer between two devices. Performance. The performance of a computer system is based on hardware design of the processor and the instruction set of the processor. To obtain high performance of the computer system, it is necessary to reduce the execution time of the processor. Execution time is equals to, it is defined as the total time required executing one complete program. The processing time of the program includes time taken to read inputs, display outputs, system services, execution time, etc. The performance of the processor is inversely proportional to the execution time of the processor. More performance, less execution time, less performance, more execution time. Performance of the computer system is based on the following factors: cache memory, processor clock, basic performance equation, instructions, compiler. Cache memory. It is defined as a fast access memory located in between CPU and memory. It is part of the processor as shown in the figure. That is this: main memory, bus, processor, cache memory. The process needs more time to read the data instructions from main memory because main memory is away from the processor as shown in the figure. Hence, it slows down the performance of the system. The processor needs less time to read the data and instruction from the cache memory because it is part of the processor. Hence, it improves the performance of the system. Processor clock. The processor circuits are controlled by timing signals called as clock. It defines constant time intervals and are called as clock cycles. To execute one instruction, there are three basic steps, namely fetch, decode, and execute. The processor uses one clock cycle to perform one operation as shown in the figure. Clock cycle T1, T2, T3, instruction fetch, decode, execute. The performance of the processor depends on the length of the clock cycle. To obtain high performance, reduce the length of the clock cycle. Let P be the number of clock cycles generated by the processor and R be the clock rate. The clock rate is inversely proportional to the number of clock cycles, that is, R is equals to 1 by P. Cycles per second is measured in Hertz, 500 megahertz, 1.25 gigahertz. Two ways to increase the clock rate is to improve the IC technology by making the logical circuit work faster so that the time taken for the basic steps reduces. Reduce the clock period P. Basic performance equation, let T be the total time required to execute the program, let N be the number of instructions contained in the program, S be the average number of steps required to one instruction, R be the number of clock cycles per second generated by the processor to execute one program. Processor execution time is given by T is equals to N into S by R. This equation is called as basic performance equation. For the programmer, the value of T is important. To obtain high performance, it is necessary to reduce the values of N and S and increase the value of R. Performance of the computer can be measured by using benchmark programs. SPEC, System Performance Evaluation Corporation, is a non-profitable organization that measures performance of the computer using SPEC rating, System Performance Evaluation Rating. The organization publishes the applications, programs, and also time taken to execute these programs in standard systems. SPEC is equals to running times of the reference computer divided by running time of the computer under test. Difference is multiprocessor and the multi-computer. Multiprocessor is a process of interconnection of two or more processors by means of system bus. It is a process of interconnection of two or more computers by means of system bus. Uses common memory to hold the data and instruction. Multiprocessor. It has its own memory to store data and instruction. Complexity in hardware design. Multiprocessor. No much complexity in hardware design. Multi-computer. Difficult to program for multiprocessor system. Easy to program for multi-processor, multi-computer system. Memory locations and addresses. Memory is a storage device. It is used to store characters, operand, data, operands, and instruction. It consists of number of semiconductor cells, and each cell holds one bit of information. The group of 8 bits is called as byte, and a group of 16 or 32 or 64 bits is called as word. Word length 16 for 16-bit CPU, word length 32 for 32-bit CPU. Word length is defined as number of bits in a word. Memory is organized in terms of bytes or words. The organization memory for 32-bit processor is as shown in the figure: n bits. First word, second word, ith word, last word. Contents of memory location can be accessed for read and write operation. The memory is accessed either by specifying address of the main memory location or by name of the memory location. Address space is defined as the number of bytes accessible to CPU, and it depends on the number of address lines. Byte addressability: each byte of the memory are addressed. This addressing used in most computers are called byte addressability. Hence, byte addressability is the process of assignment of the address to the successive bytes of the memory. The successive bytes have the address 1, 2, 3, 4 until to power n minus 1. The memory is accessed in words in a 32-bit machine. Each word is 32-bit and the successive addresses are 0, 4, 8, 12 and so on. Address 32 bits. 0, 0, 0, 0, 0th bit, first byte, second byte, third byte. Big Indian and Little Indian assignment. Two ways in which byte addresses can be assigned in a word. Two ways in which a word is stored in the memory. Big Indian, Little Indian. Big Indian assignment: word address 0, 4, 2 power k minus 4. Byte addresses in zeroth column 0, 1, 2, 3, 4. 4 is 4, 5, 6, 7. 2 power k minus 4, 2 power k minus 3. In this technique, lower byte of data is assigned to higher address of the memory, and higher byte data is assigned to lower address of the memory. In this technique, lower byte of data is assigned to higher address of the memory. Higher byte of data is assigned to lower the memory. The structure of memory to represent 32-bit number of the big Indian assignment is as shown in the above figure. Little Indian, in this technique, lower byte of data is assigned to lower address of the memory. Higher byte data is assigned to higher address of the memory 3210. 7654 to power k minus 1 to power k minus 2, like this. Lower byte of data is assigned to lower address of the memory. Higher byte of data assigned to higher address of the memory. Store a word John Cena is in memory starting from word 1000 using Big Indian and the Little Indian method. Big Indian John Cena, we have it as 10000 1004 for each Big Indian and the Little Indian. For John Cena, we have from 0, 1, 2, 3, 4, 5, 6, 7. But for this, we have 3210 Little Indian. It's like this. Word alignment will be word size 16-bit, 32-bit, 64-bit. The structure of memory for 16-bit CPU, 32-bit CPU and 64-bit CPU are as shown in the figures 1, 2 and 3 respectively. For 16-bit CPU, it is 34, 65H and something. 16-bit, it will be addressing will be 5000, 5002. 34H, 65H, 86H. Those are the data. And the addresses will be of like 5000, 5004 for 32 bits and 64 bit 5000, 5008, 5016, 5024, like that. This the process of assignment of the addresses of two successive words, and this addresses the number of bytes in the word is called as word alignment. Accessing characters and numbers. The character occupies 1 byte of memory and hence byte address for the memory. A number occupies 2 bytes of memory and hence word address for numbers. Memory operation. Both program instructions and operands are in the memory. To execute, each instruction has to be read from memory, and after execution, the results must be written to memory. There are two types of memory operations, namely memory read and memory write operation. Memory read operation, load, read, fetch. Memory write operation, store and write. Memory read operation, it is a process of transferring of one word of data from memory to accumulator, GPR. It is also called as memory fetch operation. Memory read operation can be implemented by means of load instruction. The load instruction transfers one word of data. One word equals to 32 bits from memory into accumulator as shown in the figure. Memory into accumulator. It is read operation. Then steps for memory read operation. The processor loads MAR memory address register with the address of the memory location. The control unit of the processor issues a memory read control signal to enable the memory component for read operation. The processor reads the data from memory into the accumulator by means of bidirectional data bus MAR memory accumulator. Memory write operation is the process of transferring of one word of data from the accumulator to the memory. The memory write operation can be implemented by means of store instruction. The store instruction transfers one word of data from the accumulator to the memory location as shown in the figure. Step for memory write operation. The processor loads MAR with the address of the memory location. The control unit issues the memory write control signal. Then the processor transfers one word of data from the accumulator to the memory location, which is pointing to by means of bidirectional data bus. Computer operations and instructions and instruction execution. Computer is designed to perform four types of operation, that is namely data transfer operation, ALU operation, program sequencing and control, IO operation. Data transfer operation. Now here it will be data transfer between two registers. Opcode source 1 destination. Processor move instruction to perform data transfer operation between two registers. Mathematical representation of the instruction R1, R2, move R1, R2. R1 and R2 are registers only, where move is the operation code, R1 is the source operand, and R2 is the destination operand. This instruction transfers the contents of R1 to R2. Before the execution of move R1, R2, the contents of R1 and R2 are as follows: 34H and 65H. After the execution of move R1, R2 command, the contents of R1 and R2 are as follows: R1 is equals to 34H and 34H. Data transfer from memory to register. That will be the processor uses load instruction to perform data transfer operation from memory to register. The mathematical representation of this instruction is load A ACC, where ACC is the accumulator, opcode operand, load loc. For this instruction, memory location is source and the accumulator is the destination. Data transfer from accumulator register to memory. Process users store instruction to perform data transfer operation from accumulator register to memory location. Mathematical representation of this instruction is ACC loc A, where ACC is the accumulator, format opcode and operand, store loc A. This is for accumulator to memory, memory to register load, and register to register move. ALU operations. The instructions are designed to perform arithmetic operations such as addition, subtraction, multiplication, division, as well as logical operations such as AND, OR, and NOR operations. Add or not R1. The mathematical representation of this instruction is as follows: R1 is equal to contents of R0 plus R1. Contents of R1. Adds the contents of R0 with the contents of R1 and result is placed in R1. Subtract R0, R1. The mathematical representation of this instruction is as follows: R1 is equal to R0 minus R1. Subtracts the content of R0 from the content of R1. and result is placed in R no R1 here and R not R1. It logically multiplies the contents of R1 R naught with the content of R1. Result is stored in R1. R no 1 is equals to R naught and R1 multiplies it. Not R naught. It performs a function of complementation. IO operation. Instructions are designed to perform input and output operations. The processor uses move instruction to perform IO operations. Input device consists of one temporary register, that is data N register, and output register consists of one temporary register called as data out register. Input operation, it is the process of transferring one word of data from data N register to processor register. The mathematical expression is R not data N. Output operation, it is the process of transferring one word of data from the processor to the processor register to data out register. Move R naught to data out. The mathematical representation of this instruction is as R naught to data out. Register transfer notation. There are three locations to store the operands during the execution of the program, namely one register, memory location, IO port. Location is storage space used to store the data. Instructions are designed to transfer data from one location to another location. Consider the first statement to transfer data from one location to another location. Transfer the contents of memory location whose symbolic name is given by amount into processor register R naught. The mathematical representation of this statement is given by R naught amount. Consider the second statement to add data between two registers. Add the contents of R naught with the contents of R1 and result is stored in R2. Mathematical representation of this statement is R2 equals to R naught plus R1. Such a notation is called register transfer notation. It uses two symbols, a pair of square brackets to indicate the contents of the memory location, and two is the arrow to indicate the data transfer operation. Assembly language notation. This is register transfer notation. Assembly language notation will be consider the first statement to transfer data from one location to another. Transfer the contents of memory location whose symbolic name is given by amount into processor register R0. The assembly language notation of this statement is given by move upward amount source R0 destination. This instruction transfers one word of data from memory location. Symbolic name is given by amount into the processor register R0. This instruction transfers one word of data from move amount, R0 from memory location whose symbolic name is given by amount into the processor register R0. The mathematical representation of the statement is R0 is amount. And the second statement at R0, R1, R2. Consider second statement to add data between two registers. Add the contents of R0 with the contents of R1 and result is stored in the R2. The assembly language notation for this statement is given by this opcode source 1, source 2 and destination. The instruction adds the contents of R0 with the contents of R1 and result is stored in R2. The mathematical representation of the statement is given by R2 equals to R0 plus R1. Such notations are called assembly language notations. Basic instruction type, there are three types of basic instruction, namely there are three types of basic instructions, namely 3 address instruction format, 2 address instruction format, 1 address instruction format. Consider arithmetic expression z is equals to a plus b, where a, b, z are the memory location steps for evaluation. Access the first memory operand whose symbolic name is given by a. Access the